Amazing. Well, good evening, Gophers, and thank you very much, London Gophers Meetup, for having me on here. So yeah, this is my talk, Thinking with Portals of Performance Optimization, Goroutines, and Comedy Puzzle Video Games. I like it when I receive interesting problems. And by interesting problems, it normally comes down to it's broken. And in this current when the example I'm about to use, what was broken was one of our services. We received word that a dashboard that we own wasn't responding. And when we looked into the graph that showed how much work was being done or how long it was, and specifically how long it was taking, we could see that we were hitting sometimes close to 20 seconds, which is real unfortunate because there is a hard timeout limit at 10 seconds. So anything that took longer than 10 seconds was failing, which is why the dashboard wasn't working. Oh dear. We actually launched this dashboard in March, and it was a bit of a creeping problem. We can see in July that it was taking about 5 seconds. In October, it was taking about 8 seconds, and then suddenly you hit November and it's hitting the timeout limit. So what was happening? Well, it's not a particularly complicated setup. You've got a user, you've got some code in the middle, and you've got a database on the other side. The user asks the code for something, the code gets the data from the database and returns it. And inevitably, the slow part, the part that was causing our timeouts to happen, well, it's this bit in the center. And this is roughly the flow that was happening. Now, because Google Slides has a completely awesome set of animation tools, I'm going to be animating it like so. Wait for it, there we go. So what would happen is a request would come in and search up a bunch of riders. Then for each rider, it takes the first rider, it goes to the database and gets some details about it, and then it returns it. Then once it's done that, it gets the details for the second rider and it goes to return it. And by now, I'm sure you can see where the problem is, that well, whilst it's all well and good when we first started the service, there wasn't too many riders, it could make all the requests quite quickly and then go and email it off. Well, suddenly when we had a much higher load, this doing it sequentially was causing us to be way too slow. And so then this is how we would like to performance optimize. We still have to get the riders as before, but instead of doing all the rider requests one at a time, we will, yes, I am using copy and paste. We will do them all at once. So rather than making 3 requests and waiting for each one to be done, you can instead make, well, effectively let the 3 requests happen at the same time and do it in a fraction of the time. And then you can, once all the requests have been made, you can go and email it off to your heart's content. And so the way that we ended up implementing this in Go was with Goroutines. And I like using mental models. And so this little figure here represents our Goroutines. You can also, in this context, call him a Goroutine. Though we're just going to go with calling him you could also call him a worker. And the thing about Go and these Goroutines and these workers is that Go can have a lot of them. And actually, they are all spun up in their own little mini cubicles, and they're quite happy there. They don't talk to each other. They don't see each other. They're not even aware each other exists. And yet they are all still doing work. And so what we'd really like to happen is that we have our 3 riders. If we hand each rider to one of the workers, then the workers can get the data and send it all back. And that's how we can split the work up. But what are these magic arrows? How do you, I've already said that, all these workers are completely separated and isolated. How do you get data to and from them? Well, that's where we use what Go calls channels. But what's a channel? And this really was the inspiration behind this talk, because should you visualize channels like on a TV, something that it's tuned into? Perhaps you should think of it like a tunnel that goes under, between England and France. Well, how should you visualize a channel? And this is where I hit upon the metaphor that works best for me: portals. If you haven't played it, Portal is an absolutely wonderful puzzle comedy video game. But the concept behind portals is that these 2, red and blue, orange and blue, link space. So if you put your hand through one, it comes out of the other. So you can move your stuff between two different spaces without actually connecting the spaces together. So say we have a Go routine, a worker on the left that wants something from the worker on the right. We can open up two portals between them, and the worker on the right can pass the work through to the worker on the left. All great. But what happens if there is no one on the other end? Because when we open a portal, there has to be two sides to it. So if our worker on the right tries to pass something through, well, it's just going to be waiting there. And if you try, it will just hold there because it's been told to pass it through to something on the other side. And since there's nothing on the other side to take it, our work is just going to be stuck. You can use something, Go has a concept of buffers. And so, a bit like a sort of a plate on like a sushi conveyor belt, you could have it so that a buffer allows you to pass some items through without anyone strictly being there to fill it up. But it's still possible to hit the situation where you've got no more plates left to fill and your worker still wants to pass something on. And this will cause your worker or your Go routine to completely halt if nothing can take off the channel. And so too for the other side, if your worker has been told to await a message, well, it's just going to wait for a message. And if a message never comes, it will be very sad. So to summarize, if you're trying to pass something down through the portals or down a channel, there needs to be something on the other side to receive it. And if something's waiting to receive, it's not going to be able to do anything until there is data ready to be passed down it. And so bringing it back to our example with our riders, what we can do is we can open up one portal where the riders come in, and then portals to all these different Go routines. And so we can pass a rider through to one, pass a rider through to the other, and then pass a rider through to the final one. And they can all be worked on and done separately. But what happens if a fourth rider comes along? We try to pass it through and actually it's going to wait because, well, there's no worker free to pick it up. And actually, this is the behavior we want. We don't since all of our working tasks are full, well, our rider is just this new rider is just going to wait until one of them's free. So when sometime later, one of our workers is free, it will then pick up the new rider. And this is actually quite desirable behavior. It means that we can be quite clear about how much work is going on and how much is being operated on at one time. And the crazy thing about these portals is we don't need to just have one of them or two of them. We can have as many as we want and we can link them all together. So we can end up in this, what looks like a Where's Wally kind of art page, but it's completely workable. You've got a rider waiting to be processed. You've got a rider being taken off the queue. You have a rider being worked on. You have data being passed. Once a rider's been processed and got data, you have it being passed. And then you have another worker that's collecting all this data and it can aggregate it and send it off, etc. And at the end of all of this, after implementing Go routines, what used to be taking 10, sometimes close to 20 seconds, now down to less than 2 seconds. And in the wise words of Cave Johnson, I punched those numbers into my calculator and it made a happy face. Thank you very much.